Alright, so in this video I'm going to show you how to solve for concentrations at equilibrium when only initial concentrations are given and K is given. So in the last type of problem, K was not given and you were given at least one equilibrium concentration. So for these types of problems where we have all initial concentrations and then only K, you're going to need to use the quadratic equation to solve or approximation. So you're going to follow this process. You're going to write the Kc or the Kp expression. If initial concentrations of the products are given, you have to solve for Q before you actually make your ice table. Now, if they're not given of the products, so if the initial concentration of the product is not given, then you can assume it's 0. So you're going to create your ice table. And then once you get your ice table, you're going to plug the values that you get for E into the K expression. And then basically at that point you're either going to put it into ax squared plus bx plus c and use your calculator, or if K is small you can use something called approximation, which I'm going to show you. Alright, so if your initial concentrations of the products are not given, you can assume it's 0. But if they are given, you have to solve for Q first. And then if Q is greater than K, then you're going to subtract reactants and add the products in your C section of the table. And if Q is greater than K, you're going to subtract the products and add reactants. Alright, so find the final concentrations of all species once equilibrium has been established. If Kc is this, and then the concentration of HF is 2. Alright, so what we're going to do first, we're going to write out our Kc expression. So Kc is equal to the products, so hydrogen multiplied by fluorine divided by our reactants, so HF, and that is going to be squared. Alright, so we have our Kc expression. So now let's look at our ice table. Okay, so initially the concentration of HF was 2. Okay, so that's our reactant. Remember, if the products are not given, you can assume that it's going to be 0 for the initial concentration. Alright, so now since products are initially 0, that means we're going to start making products and taking away the reactants to do that. So you're going to subtract your reactants. So it's going to be minus, and since the coefficient here is 2x, and we're going to be adding the products, no coefficient, so it's just x. Alright, so now we can put these together. So no equilibrium concentrations were given here at all. So we're just going to simply put the I with a C. So 2 minus 2x, 0 plus x, so it's just x and x. Alright, so now that I have this part, what I'm going to do is I'm going to plug it into this Kc expression. So once I do that, I'm going to have Kc is 1.5 times 10 to the negative 5th, and that's equal to H2, which is x. So you're plugging the E expressions into your K equation. So x, and then F2 is also x, and then divided by your HF, so 2 minus 2x, and that's going to be squared. Alright, so now at this point, what I'm going to do is I'm going to put it into ax squared plus bx plus c is equal to 0. Okay, and once I do that, then I can figure out what x is and get all of my concentrations. So let's do that. So here's what I'm starting with. All right, so at this point, x times x is just going to be x squared. And this is 2 minus 2x times 2 minus 2x. All right, so now what I'm going to do, I'm going to expand this out. I'm going to FOIL. X squared. Okay, so 2 times 2 is 4. 2 times negative 2x would be negative 4x. Negative 2x times 2 would be negative 4x. And then negative 2x times negative 2x would give me a positive 4x squared. All right, so at this point I can also combine these together. So 4 minus 8x plus 4x squared. All right, so now let's just move this onto the other side. So multiply both sides by this. All right, and then we're going to multiply this out. So 1.5 times 10 to the negative fifth times 4 would give me 6 times 10 to the negative fifth. Negative 8 times this would give me negative 1.2 times 10 to the negative fourth x. And then 1.5 times 4 x squared would give me 6 times 10 to the negative fifth x squared. And that's equal to x squared. All right, so now I'm going to move this onto the other side because remember, overall it needs to equal 0. So I'm going to subtract this out. So I should get 0 on this side. And then these are both x squared, so I can go ahead and just combine those. So negative 1 plus 6 times 10 to the negative fifth will give me, or not times, I'm sorry, you're adding them together. So that's going to be negative 0.99994 x squared. All right, so, and it looks like we have our expression now. So remember, you should have something times x squared, and then the number by itself. All right, so, well, this is with the x squared, so that's our a. This is our b with our x, and then this is our c. So we're going to plug this into our solver, and once you do that, you should get x is equal to 0.0077. All right, so now I've got this. Now I need to go back and get my concentrations. So I know that if I look here, I know that x is equal to this. So now I can just plug it into these expressions to get the actual concentrations here. So for HF, 2 minus 2x, so 2 minus 2 times 0.0077. Let's go ahead and put that in the calculator really quick. Okay, so 2 times 0.0077 gives me 0.0154.
Ms. McCollum, please come to the dean's office with the student's phone. The parent's here to collect it. Ms. McCollum, please come to the dean's office to bring the phone. The parent is here to collect it.
All right, so concentration of HF is equal to 1.9846. Still pretty close to 2. So now I've got the concentration of that. Well, X is equal to H2 at equilibrium. So X, or the H2 concentration, is also just equal to 0.0077. So if at equilibrium it's just X, once you find X, you know what the concentration is. You don't have to plug it in anything. All right, and now we have our concentrations. Now, there's actually something that we could do instead of having to do a lot of math. Okay, and this is because K is very small. So you can use something called approximation when K is very, very small. So if it's less than 1, you can do this. You can assume X is very, very small, and you can actually cancel X out when it's being added or subtracted. So let's go back to our original K expression when we plugged everything in. For the last one, it was 1.5 times 10 to the negative fifth x squared over 2 minus 2x squared. Okay, so when I look at this, K is very small. It's less than 1. So that means that when I'm doing this, when I subtract something that's very small or very, very close to 0, it's just going to be itself. So we can kind of actually just take this out because it's being subtracted. So if it's being added, X is being added or subtracted, you can just simply cancel it out, provided you have another X somewhere else. So if it's being multiplied, you cannot do this. All right, so at this point, it's 1.5 times 10 to the negative fifth is equal to x squared over 2 minus 0 squared. Well, 2 squared would give me 4. Oh, and now it looks so much easier to deal with. So now you just multiply it out. You're going to get 6 times 10 to the negative fifth is equal to x squared. And then to solve, you just take the square root. And you do get the same, almost the same value. So it's about 0.007. And this is a completely legitimate way to solve these types of problems, and they accept it on the AP exam as well. So this only applies, though, if K is small, and you can only take it out when it's being added or subtracted, and provided that there is another X somewhere. All right, so let's look at another equation. Initially, if there's 1 mole of H2, 2 moles of F2, 0.1 moles of HF, Kc is given, it wants to know, it should say this, but it's asking for equilibrium concentrations. All right, so first thing, let's write our K expression. So Kc is equal to our products over our reactants, and this should be squared because there's a coefficient of 2. All right, so now we're going to set up our ice table. So I, C, and then E. All right, so initially there is 1 mole of H2, 2 moles of F2, and 0.1 moles of HF. Okay, so now this is different because I'm actually given an initial concentration of the products. So that means solve for Q first. Before you move any further on your ice table, solve for Q. Remember, Q is the reaction quotient, so this is the concentrations of the products multiplied or divided by the concentration of the reactants at any time during the reaction. So I'm going to start with this, and I need to see which way is the reaction going to shift. Am I going to be making products, or am I going to be making reactants? So Q is the same expression as K. The only difference is Q is at any time at all during the reaction. So it's not necessarily at equilibrium. All right, so Q is equal to 1 multiplied by 2 divided by 0.1 squared. And when I do this, I get Q, I get 200. It's way big. So here, Q is greater than K. So if Q is greater than K, the number is too large. So that means the numbers on the top are too big. So since my products are larger than they should be, I'm going to go back and move to the reactant side. So when Q is greater than K, I go to the left of the equation, or the reactant side. I'm going to be creating reactants in this case. So when I go and I make my ice table, if I am creating reactants, and here I am actually going to be adding on my reactant side and subtracting on my product side. I'm doing that because reaction is going to shift in this direction to make the reactants, so I'm adding them, and then in order to do that, I'm taking the reactants away. So this is going to be adding this time, and it's going to be 2x because of the coefficient, and we're taking this one away, taking this one away. So at equilibrium, it's going to be 0.1 plus 2x, 1 minus x, and 2 minus x. All right, so now I'm going to plug everything into the equation. All right, so my K value was given. It was 0.00768 or 77. And that's equal to 1 minus x times 2 minus x divided by 0.1 plus 2x squared. And if you go back to your ice table, remember, we're plugging these values into the K expression, and then that's how we came up with what we just did. All right, so now we're going to expand everything out. Oh, we cannot use approximation here because all of the x's are actually being subtracted or added, which means technically if I were to take this out, and this out, I have nothing to solve for, so that's not going to work. A lot of times you will be able to use approximation, just not in this case. All right, so let's go ahead and start expanding everything out. So 1 times 2 will give me 2. 1 times negative x will give me negative x. And then I get 2 times negative x, which is negative 2x. And then negative x times negative x would give me x squared. Okay, so if this is what I have, if it's being squared, this is what it will be when it's expanded. Okay, so now I'm going to multiply everything out. So 0.1 times 0.1 would be 0.01. 0.1 times 2x would be 0.2x. 2 times this would be 0.2x. And then 2 times 2x would be 4x squared. All right, so I can combine a few terms here, so let's do that. Negative x plus negative 3x would be, or 2x would be negative 3x. All right, so then I can combine these, the x's here. Okay, so now let's move this to the other side of the equation. So take the bottom, multiply it out. It'll cancel. Okay, so multiply that out. And so 0.00768 multiplied by this would give me 7.68 times 10 to the negative 5th plus 0.03072x plus 0.03072x squared. And that's equal to 2 minus 3x plus x squared. All right, so now I've got this expression here. Move everything to one side, so I'm going to subtract all of it. So you need to be really careful about your negative signs here. You're subtracting everything in here. So that means I'm subtracting 2. I will have a positive 3x here. I will have a positive 3x.
Miss Rosa, please come to the front office. Miss Rosa,
And then
please
a
come to the
negative
front office.
x squared. All right, so now if I combine everything together, put the whole numbers with the whole numbers, so 1.999, which is what you get here, or I'm sorry, negative. And then here we're going to get 3.003, all that, x, and then we're going to put the x squareds together. So minus 1 plus this. Okay, so you're going to get negative 0.96928 x squared, and that's all equal to 0. All right, so now we have our values. We have, let's see, our A, we have our B, and then we have our C. All right, so once I do this and I plug it into my solver, I'm going to get a number. You're going to get 0.563. All right, so that's my x value. So x is equal to 0.563. And then I'm going to go back and solve for my equilibrium amount. So 0.1 plus 2 times this. 1 minus this. And then 2 minus 0.563. All right, so when you do this, you get 1.22, and then you get 0.437, and then you get 1.437 here. So the concentration of this is 1.4 roughly. H2 will be this, and then HF will be this.